Okay, well, thank you all for being here, getting up early on a Tuesday morning. As Esther said, I'll be doing an overview of the work being done within the Center for Electrochemical Energy Science. The first thing I'd like to do is thank Dan Sherrison for pulling together this the Electrochemical Energy Summit. It's a really nice time to get a snapshot of the centers. Of course, yesterday we had the energy storage hubs talking, and today we'll be hearing about the work from the various energy frontier research centers. The CEES, so the Center for Electrochemical Energy Science, is one of the EFRCs which is continued, where although the character of the center has changed somewhat, and the subject matter as well. So what I'd like to do is give you a sense for the kind of work that we're going in. A lot of it is sort of work in progress, because the work that we've been doing has been going on for about a year. So you'll see some things I'll be talking about a little bit more depth than others. So here we go. So I thought I would start with, since this is a the first session for the Energy Frontier Research EFRCs, I'd give a kind of a brief overview of some of the motivations. I don't think the energy storage is a really a challenging area. I mean, in many ways, what we're competing against is gasoline. So this is a plot from Stan Whittingham's MRS Bulletin article from some years ago, plotting various technologies for energy storage as a function of energy density and power density. Gasoline and the internal combustion engine really is really the defining technology. You have batteries which have comparable energy densities, and things like supercapacitors which have comparable power densities, but neither of these electrochemical systems give both. And so in a lot of ways what we're trying to do is get to the point where we can bypass the internal combustion engine, which of course is also getting better with time as well. Sort of batteries and supercapacitors are these two end-member technologies. In some sense, they look similar. You have electrodes, electrolytes, you're moving ions back and forth. Although in the case of batteries, you tend to move ions into electrodes and do insertion and reactions. And supercapacitors, it's more of an adsorption reaction, thereby giving the higher power. So here's just a very simple schematic of how a battery operates. You have on the left the anode, you have the electrolyte and the cathode. Typically this is an organic liquid electrolyte. This would be the battery in the discharged circumstance. I'll mention in passing that CEES-1 had mostly a focus on anodes, and typically things like silicon and carbon type structures, and trying to understand how to handle some of the challenges of carbon. And CEES-2, we're focusing more on the cathode side, or the oxides. So when you operate a battery, you're shuttling lithium ions back and forth between the anode and the cathode. And one of the factors in this process is, as you can see schematically, you have things like volume changes. So you have mechanical stresses, in addition to the challenges of just getting the ion in and out of these structures as well. And on top of that, you also have instabilities. For instance, the electrolyte can decompose, and so you can get what's called the solid electrolyte interphase, which is widely studied on the anode side, and in fact is needed for the stable operation of a graphite anode. But depending on the voltage of the cathode, one can expect something similar to be going on the cathode side as well. So in the broader societal sense, if we can drive developments in energy storage, there are two areas really where there could be very substantial impact. One is in renewable energy. If we can do large-scale storage of energy, then we can effectively use things like solar energy and wind energy. So, for instance, the variable load on the grid could just be used by storing the energy during the day and then using it at night, for instance. Also, consumer products are really a big driver as well. I think we all have in our pockets one of these cell phones, which I think, the one thing about working in this area, which I really enjoy, is that when you tell your neighbor that you're working on energy storage, everyone immediately says, if only my cell phone were, could have a charge twice as long or things like that. And so it really connects with people. But of course, transportation is another big area that this could impact as well as things like medical devices and so forth. And so the Tesla is really the I think in a lot of ways the archetype of the electric vehicle. I mean, from what I understand, I haven't had the pleasure of driving one yet, but what I understand, it's a phenomenal car to drive, and and inside each one is roughly 8,000 of these 18650 cells. So if you imagine if you can, get a factor of 2 improvement in the energy storage of your system, you can, drop this in half. So, so you can just imagine, there's a substantial cost savings from that and engineering. But if you look inside the these batteries as well, you can see, so this is, so the electrodes are jelly rolled inside, so you have these sheets where you have the anodes and cathodes. So these are the current collectors, the copper and aluminum, then you have the anode here and the cathode there. And if you look, this is a compositional map. You can see these things are really complicated things. And I think it's a miracle that these things have been developed as well as they have. From my own sense, I'm not actually particularly good at understanding things that are this complex. And so, so one of the themes of CEES, of the work that we're doing in CEES, is to try to simplify these systems to the point where we can really extract out all the information that we like about what the chemical processes are that take place as you're shuttling lithium between these electrodes. So, and I think the other point, which I think is very interesting about if you think 2 technologies that we know a lot about personally, like computers and batteries, over the past 40 years, computers have had roughly a million-fold improvement, whereas over the same time period, batteries have increased in capacity or whatnot by a factor of about 5. Right, so I think part of this is that this is one technology largely that's just been scaled, whereas improving batteries involves coming up with new chemistries and really pushing the limits of what you can do with the material. And finally, there's the issue of safety, which that these batteries are flammable. They have secondary reactions or whatnot. And I think if you Google lithium-ion battery fire, there's like hundreds of pictures that come up. There are various things like spontaneous laptop fires. The one that's probably scariest to me is, of course, the plane. This is a UPS plane that was shipping lithium-ion batteries, and it spontaneously caught fire. Right. So if you think about how many batteries are in a typical plane that people are just charging up just before they get on the plane. That it's a little bit scary. So okay. So what I'd like to do now is to sort of transition into what CEES is doing and who we are. This is a picture from our first all-hands meeting from about a year ago. CEES is a collaboration of 4 institutions: Oregon National Labs, University of Illinois Urbana-Champaign, Northwestern University, and Purdue. If you see this little schematic map up here, one of the nice things is that we're geographically relatively close by, which means that we can go back and forth and meet each other as needed. We can, and so it's good for communications, although we also make a lot of use of things like web meetings and things of that sort as well. This is the PI team. This is organized in our task structure. We actually have 2 types of organizational structures in the center. So on the left are the group of people who are largely focused on characterization and understanding of systems through either experimental or computational studies. And on the right are the people who are the materials people, the people who create materials and that we can study. So this is a nice diverse group of people with distinct skills. So this now is I think the the driving force for the center as a whole. We've chose as our mission is to understand the electrochemical reactivity of oxide interfaces, materials, and thin films. And with a focus on understanding what are the limitations of battery performance. So the key point, I think, in the center is that the motivation is improvements in lithium battery technology, but what we're trying to do is focusing on the understanding. And so we're we need a better battery, I think, with it. So we're trying to get a robust understanding of these processes, and we're going to use novel approaches to do this. And there's a theme running through the center of understanding interfacial reactions as well. So we try to create materials with well-defined interfaces. We're trying to use materials architectures and nanostructured materials, for instance, like thin films and multilayers. And we're also trying to ultimately to try to direct the electrochemical reactivity to have the materials do what we want them to do, as opposed to what they may do on their own. And so to achieve this also, we have a big emphasis on state-of-the-art tools such as X-ray probes, electron microscopy, high-level computation, and as I mentioned before, various growth methodologies like atomic layer deposition, pulse layer deposition, and so forth. So what we're hoping is that by looking at the kind of model systems and the focus on understanding, the hope is that, if you think of, I think of sort of the challenge of lithium-ion batteries as a big mountain range. We're trying to get to the other side. A lot of people are trying to find the paths to go over. That you can see. We're looking for that tunnel that might go through somewhere. So maybe we'll fall on our faces, but I think we're going to learn a lot of stuff in the meantime. And because I think these materials are really interesting in the sense that we're really driving them. There's a lot of non-equilibrium behavior, and if we can understand this, I think there's a lot of things that we can that we'll learn. So, as I mentioned, there were the two major tasks, which were the characterization and the materials. We also have three research themes, and so the research themes are the ones that are focused on particular material systems that we're focusing on. The first one is to look at insertion reactions of inserting lithium into metal oxides, and so we're taking lithium manganese oxide spinel as our standard material. This is a material which has a well-known this is basically a technology, right? So although it has some problems, and so it has a well-known capacity, lithium capacity, you can, in parentheses, are a rough estimate of the energy storage of the material. But there, as I'll describe in a second, there are limitations to this, and ultimately we want to try and use interfacial modification to control this reactivity. A second type of reaction that we're looking at are conversion reactions, and this is where when you insert lithium into a metal oxide, you get metal nanoparticles and lithia embedded in a lithium matrix. And there's been a lot of work on these types of systems. This is a system which has a much higher lithium capacity because it's not limited crystallographically, but it's as a substantially lower voltage. But nevertheless, if you could get this voltage, it would be a substantial increase in energy storage, which would be great. But conversion reactions have a lot of challenges. One is the fact that because you have this, the conversion reaction itself, there's transport, there's nucleation. The first cycle is typically very different from the second one. You have overpotentials. So in general, we're trying to see if we can control these reactions with nanophase confinement. The third type of reaction is by far the most aggressive in terms of what we hope to do, and where there's the least known. And these are what we call hybrid reactions, which are a mixture of lithium-ion and lithium-oxygen reactions. Lithium-oxygen was something that we were doing in CEES-1, and there's actually quite a lot of work being done in that area. Mike Thackeray came up with this idea that I'll describe towards the end of my talk, with the idea that if you can control both the lithium and oxygen, you can effectively go between something like hematite and Li5FeO4. So this is a really complex reaction. There's only very limited validation, and so we're trying to see what we can do with this. If this were possible, this would have a very substantial increase of energy density with respect to what the what LMO does now. So I'll first now go into some of the work that we're doing with LMO. And so ultimately, one of the questions is, if we can control this reaction, can we effectively double the capacity of LMO? You can see that here. In this particular slide, this is showing the variation of potential with capacity for LMO. So on the right is the empty manganese oxide spinel. In the middle is the LiMn2O4, and this is Li2Mn2O4 on the left. So as you go across here, you can see there's a change in potential for the reaction. So essentially, this is the part of the phase space which is accessed. And this transition here, where you get nucleate the tetragonal LMO phase, is associated with some various complex reactions. This is where you're getting manganese 3 in the system, and manganese 3 is susceptible to disproportionation reactions, which can lead to manganese 2, which is then soluble, then can lead to manganese dissolution. So there are various ways that you could try to fix this as a problem. What we're trying to do is see if we can control the interface and separate the interface from the electrolyte. Maybe we can prevent the manganese 2 from being soluble. So, in terms of the work in CEES 2, this is the place where we had our first initial successes. And so this is some work from Calamine's group. What he did was to add coatings on an LMO, which were titanium-containing spinel coatings. And what he found is that with these coatings on the surface, he could effectively suppress the manganese dissolution. So, okay, this is one way in which dissolution of manganese can be controlled. Andy Gewerth took a completely different approach in this, was to do electroless deposition of gold on LMO. So this is without and with the gold particles. These are SEM images, and what you can see is when you do the cycling, you can see that with the gold coatings, you get a substantial improvement of the capacity retention over a large number of cycles. So this is a completely different approach, but nevertheless was effective in reducing the capacity fade in these materials. And now there's a third approach, which was from our Northwestern colleagues, Mark Hersom and gang. Mark, one of his specialties is working with graphene, and so he was looking at LMO electrodes, which are sputter deposited on steel. They're crystalline, they form these kind of boulders or whatnot, so it's a fairly complex morphology. But nevertheless, and I think somewhat surprisingly, when you put the graphene, just put one or a couple of layers of graphene on the electrode surface, which is shown here, that actually, again, allows one to retain a lot of the capacity that one would normally lose without it. So experimentally, we found 3 different ways that we can limit the loss of capacity of these LMO cathode materials. What's missing now is why, and so that's actually a big part of our center, is understanding, what's going on and how it's going on, and that's I would say, as one of the people who's trying to answer that question, why, we're trying to keep up with the people who've actually shown how. So, this is some work from Larry Curtis's group, Hakeem Adir and Casey Lau. They're doing high-level computational work, so that they're simulating LMO electrodes in contact with the electrolyte to try to understand how the lithium interacts with the surface. So this is a really very complicated problem. One of the things that came out of, they realized pretty quickly when you look at the literature, there are actually multiple different predictions of what the LMO surface, electrode surface should look like in contact with electrolyte. But there's actually no data to show what the actual termination is. And so I think it's either 3 or 4 different structures that have been predicted at this point. So part of this will be hopefully understood by doing these computational studies. I should mention, so Hakeem is going to be talking about this on Wednesday, and so please go to his talk. So we're trying to now do validation, understanding what's going on. So the challenge here is that to really get the high-level understanding of the electrode-electrolyte interface, one approach is to use X-ray reflectivity, which is my own specialty. This is work being done by Xiao Chen, who's a graduate student at Northwestern that we share with Mike Bezic. And so these are LMO films grown on strontium titanate, epitaxially grown. You can get nice AFM images, typically flat. The reflectivity data, you see these high-frequency fringes, which is from the thickness. And ultimately, this data will tell us about the details of the structure of the LMO surface and how it interacts with the electrolyte. We're not yet, we haven't solved this data yet, but here are some model calculations on the right for the different types of terminations. You can see the calculations all look somewhat different, so that tells us we have sensitivity to what the termination is. In fact, I suspect that this green one is actually one that's going to be the likely answer, and the reason why you can see that is if you notice there's these modulations here, there's kind of a node right around this point. In the calculations, and this is this is an effect of termination of the LMO. And if you look at the data, you can see there's a similar node in the experimental data over here. So there's a lot of information, but I think what my sense is, anyway, we should be able to understand in detail what the structure is. One of the challenges of this, though, is that this is now on a non-conducting substrate, so we can't do electrochemistry. So this has actually been straightforward to grow LMO on some flat surface. What's much more challenging is to grow LMO on a conductive buffer layer, so we can do electrochemistry. This is something we're making progress on. This is an example of work that we did on LMO grown on indium tin oxide on yttrium stabilized zirconia. You see from the AFM that you actually don't get a film, you get actually getting a bunch of nanoparticles growing. Nevertheless, because it's a conductive layer, we can do electrochemistry, and you can see we're going all the way from like the 4 volts down to 3 volts, so we're putting 2 lithium in and pulling it back out. And this is X-ray diffraction from this in situ during the process. And this little red peak here as it's going back and forth is the lithiation, delithiation of the LMO. So this is essentially bulk diffraction of oriented particles. What we'd like to do, if we could get high resolution data, we could actually watch the lithium go in and that process of how the lattice gets destabilized. So you can see that down here we're losing capacity. So that's one of the things that's ongoing. This is other work from Jeff Elam's group. They're doing ALD growth of these materials. They're using manganese 3 precursors, alternating with ozone, and then this lithium precursor with ozone. And so by changing the relative fraction of these cycles, they can control the lithium content. So this red line corresponds to what should be LMO. We've yet to confirm that if it has the right oxidation state and structure and so forth, but that work is ongoing. Tobin Marks' group and Madeline Stalzer at Northwestern, they're actually working to design new precursors. There's actually, manganese is a really big challenge. If you want to grow LMO, you'd like to grow it in a mixed oxidation state in principle. And so you'd like to have manganese 3 and manganese 4 precursors. And so, as I understand it, there's very few precursors available for manganese, and so they've come up with these various types of these molecules, and we're testing this now to see how well we can grow materials by ALD. And lastly, with the LMO type related work, this is some work from Jeff Greeley's group looking at the actual process to try to understand that when you bring a particular molecule in, for instance, an aluminum-containing molecule, aluminum trimethyl, and to understand that decomposition and structure to create coatings at the surface, which would then be another way to try to control the instabilities of LMO. So, and Jeff Elam will be giving a talk later this afternoon about this work. So the last bit of the LMO, so this is actually not LMO work, but it's a capability that we're using. This is Andy Gwerth's group and Nancy Satos' group. There's some very interesting, so there's the combination of stress measurements, which is when you lithiate and you have your electrode on a substrate and it causes the substrate to bend, as well as strain, which is the change in volume. Typically one studies one or the other. What's, I think, an interesting opportunity is to study both of these things and to understand, so they've come up with the idea of electrochemical stiffness, which is then they can watch the lithiation process, and a lot of interesting results on this stuff, and there'll be a talk on this later this morning from Andy Gwerth. Okay, so there's a lot of work now with I think so. I hope I've given you a sense of the range of work that we're doing with these sort of model materials. The next phase is to look at conversion reactions. These are much more complex reactions, And ideally, if we can handle all these challenges, we could effectively triple the energy density with respect to LMO. So conversion reactions have been around for a while. They've been fairly well studied. Stan Whittingham's group in Nexus did a lot of work with fluorides in the last cycle of the EFRCs. They also work with various oxides. This is work from Tarasan's group. You can see this shows, I think, one of the key characteristics of conversion reactions. This is nickel oxide. You can see when you lithiate it, the observed potential for lithiation is typically around 0.6 volts, but theoretically it should be up around 1.7 or 1.8 volts. So this is a very substantial overpotential, which we'd like to see if we can control. So the general idea, one of the reasons for this overpotential is the fact that when you're lithiating, let's say, nickel oxide, you're forming nickel nanoparticles in a lithium matrix. And so this has to do with forming of a critical nucleus. And so you're creating surface area in this process. That new surface area has an energetic cost. And so that leads to, typically a sort of classic idea of critical nuclei. So you have a nucleation, you also have mass transport. So these are very complex reactions. So we're trying to, so we'd like to try to understand these things. This is some work that came out early in CEES-2 from Dravid's group. It just shows the sort of typical reactions of conversion reactions. This is cobalt oxide, where the initial phase is insertion, and then eventually you see that the material actually changes morphology until you get the nanoparticle formation. So we'd like to see what we can do with that. And so our big idea in this area is to use interfaces to try to control these reactions. That if you have pre-existing interfaces, then you can imagine that they might not need, the barrier associated with creating new interfaces might be minimized. And so maybe we could get rid of the overpotentials. And and then more generally, can we use architectures to seed these reactions? So we've developed some cells that we're doing X-ray reflectivity. So the electrode surface is shown in red here. This is essentially a beaker cell with the X-rays going through windows, and we have counter electrodes and so forth. But it allows us. This is a cell here. You can, it's about this big. You can assemble it in a glove box, bring it to the APS, and do these studies. So I'd like to give two examples on this. One is with, this is some work that's actually just been accepted in chemistry and materials. This is a chromium oxide multilayer. It has kind of an interesting history in itself, but nevertheless, what you can see, this is a TEM study from Dravid's group. You can see these well-defined layers. This is X-ray reflectivity data. There's this peak here. This is actually a Bragg peak corresponding to these layers that form. And if we solve the structure, the blue line is a fit. This is what the density profile looks like. So this is the density. This is the multilayer structure. This was actually created with a silicon, film on top, which of course is going to lithiate as well. But our focus is actually on the chromium oxide material. And so here, this is actually a block of X-ray reflectivity data. This is, as they say, in operando study. So each line is an X-ray reflectivity data set. And so you can see this yellow thing here is the Bragg peak. And this is showing the potential as we lithiate, delithiate, lithiate, delithiate. The current is shown here. So you can see that for a while, not much is happening until you're down to a relatively low voltage. And all of a sudden, you see a change in this peak position. If you think of this as a Bragg peak, the shift to smaller angles means it's expanding, as you might expect for this sort of reaction. And then when we go back up, it goes back up. You can see that it's, the reaction is partly irreversible. It doesn't quite go back to the same position, which is very typical of these types of conversion reactions. If you basically take the spectrum and solve each of those structures one by one, and you go through, you can actually watch the evolution of the electrodes. This is the electron density as a function of potential during the lithiation and delithiation. Tim Pfister is the person that drove this work. He did this really cute thing with, in addition to showing the density profiles, he color-coded the densities. So you can see what the different materials are that might produce these different things. So you can see out here, you're starting with silicon, which you're lithiating. The blue, you can see that at the starting phase, none of these densities are actually at the chromium level. So it's actually a mixed chromium oxide layer. But once we start to lithiate, you get this nice bright blue, dark blue, which it corresponds to the chromium density. And so you can also see that you're forming these low density lithia layers in between. So just from the electron density, we can see that we have these conversion reactions going on. And then we can watch it like delithiate as well. And so if we watch in detail the electron density profiles, you can see, this is the starting phase. This is after lithiation. This is after delithiation and then relithiation. So these are a couple of snapshots of the density profile. There's a lot of information in here, but if you just look at the average layer thickness in these things, you can see both the oxide and the metal. They increase and decrease and increase again, so you get the same behavior. So there's some degree of reversibility, but you can also see at the metal layer, when it increases, it doesn't quite go back to the initial layer again. So what we can see here are some of the issues causing irreversibility in these systems. Okay, so what has been so that project essentially was one of these transitional projects, kind of a feasibility study. Something that's been going on, that's going on currently right now, is work that Gena Evmenenko and Mike Bedzik have been leading, which is looking at nickel oxide, which is kind of classic conversion materials in both film and multi-layer forms. So this is, just like I showed you before, this is a block of X-ray reflectivity data as a function of time. And so, you know, you can see these Bragg peaks that show up, and those show up as the bright colors over here. And as we drop the potential down, you can see at this point we're at 0.6 volts, which is sort of the classic voltage where things happen. You can see that there's some slight changes before that, but around 0.6 volts, we just held it at this point. And then you can see that the multilayer kind of disappears, and this is because the layers get jumbled, so you no longer have regular spacing. But you still get these lobes of intensity, and those lobes of intensities are the form factors of the individual layers. You can see those lobes get small, move to smaller angle, which means they're getting thicker. Again, we have this conversion reaction. So the nickel is actually acting as a sink for the nickel in the reaction. And then after we let it sit for a while, you can see that the multilayer reforms, that all the layers start to basically order up again. So again, this is showing that we can control this reaction through this process. For TEM work being done by Dravid, they've looked at samples that have been partially lithiated as well as fully lithiated. What's very interesting here with the TEM work is that for the partially lithiated one, the multilayer itself is actually almost unperturbed except for the top layer. So we actually, in this case, at this point, we had just lithiated just the top layer of the multilayer. Although when it's fully lithiated, you can still see, there's a multilayer there, but you can also see it's been kind of chewed up a bit. And so what this led us to understand is that when these layers are forming and expanding, these things are actually not complete uniform layers, but there's actually, they're nanostructured within the planes. And so we're actually doing work now understanding that nanoparticle formation in these films. And so I think this is one more result. This is working with nickel oxide thin films. So this is a single thin film as opposed to a multi-layer. Again, we have this is the voltage, the current. This is the X-ray reflectivity data. I want to emphasize here, one point about this is that if we look at the Patterson function is just the Fourier transform of the data. For those of you who are crystallographers, it doesn't tell you the structure, but it tells you the interlayer spacings. And so what's the nice thing about that is you can kind of see when things change. And so you can see as the Patterson, as we're dropping the potential down, not much is happening here. But this line here is the theoretical potential for the nickel oxide lithiation. And down here is the 0.6 volts. I think what is very interesting is that at this 1.8 volt, we can start seeing changes in the thin film in the Patterson function. And that means that we're actually starting the reaction at that point. So I think, at least in principle, we're able to, with these thin films, access something close to the theoretical potential for the lithiation reaction, which is really one of the things we had hoped to do with these systems. And so lastly, with the conversion reactions, some work with Handan Ildirim and Jeff Greeley. They're doing computational work. If you remember, there's very simple arguments about nanoparticle nucleation, which have to do with surface energies. One of the things that we thought would be interesting to try is to understand the energetics of these systems, and so we're looking at essentially these disordered interfaces between nickel and lithiated nickel oxide to try to understand what mechanistically what these things are and whether we can get a correspondence between the energetics, for instance, that calculated from these computational approaches, with the actual critical nucleus size and nanoparticle size that we can see experimentally. So again, we're trying to make use of these the simple morphology of these materials to dig down and get a better understanding of what's going on. Okay, so that's the conversion materials. The last thing I'll mention, but only briefly, are the hybrid lithium-ion, lithium-oxygen studies. So as I mentioned before, if this were to really work, we would get maybe 5-fold improvement with respect to LMO. So the key idea of this is, as I mentioned, is some work that Mike Thackeray drove a couple years ago. So in the upper right this is the phase diagram of iron, lithium, oxygen. What you can see here is kind of an interesting characteristic of this material, which is that there's a series of thermodynamically stable phases that connect hematite down here with lithium over here. And so if you look at this reaction of written here, you can write the final product as a mixture, basically, of lithium units and hematite units for each of these phases that interconnect these two end regimes. So the excitement of this is that lithium oxygen as a chemistry is really very interesting. It has a potentially very high gravimetric energy density, but the challenge is that when you add things like oxygen tanks and scrubbers and all the things that you need to make it happen, you lose most, if not all, the benefits with respect to lithium ion. Here, the idea is that you can have a closed system and have this reaction take place without having all these other things. So potentially this could be a very interesting reaction if it can happen. But to learn more about that, I will direct you to Maria Chan's talk, which will be on tomorrow afternoon. So just to finish up then, what I'd like to just to say, I hope I've given you a sense for what we're trying to do at the center. As you see, I think we're motivated by really the problems and the challenges in battery systems, but we're trying to reduce this as much as we can to simple systems and really focus on the understanding. We have 3 different types of chemistries. So by creating materials that are very well defined, they're very simple. They're things like thin films, well-defined structures without things like carbon binders and all those things which are necessary technologically. We hope that we can extract out more understanding of what's actually going on. And so there's an emphasis on various experimental tools, sort of state-of-the-art tools, as well as making unique types of materials. And so in the end, I think what we're trying to do is probably what everybody else is trying to do in the ERFC program, is to find a way to make a transformative change in the energy storage landscape. So with that, I'll thank you for your attention. Okay, sure.
When you were talking about the multi-layer thin film, I actually have 2 questions. I couldn't tell exactly the thickness of each layer. And then my second question related to that is, did you find limitations at all of the electronic conductivity to access the materials?
Well, to give you a sense, well, this will give you, if you look, these are an angst, like for this particular one, this is an angst. Typically, the layers are of tens of nanometers, 5 to 10 to 20 nanometers. Individual layers are a few nanometers, things of that sort. So they're above molecular dimensions, but hopefully in a regime where the presence of the interfaces will be known. Transport across these things so this is an indication in this particular slide that transport's actually an issue, because the fact that we lose the Bragg peak suggests that we're getting kind of an accordion. We're stretching the accordion, but part of it's stretching before the other part. And what's actually something that we've been looking at, but which I didn't mention, I think what's been more of a challenge, I think, than the electronic transport is, if you think about it, you have the lithium transport through these layers. And it's actually, so there's some studies that Gena Evmenenko has done to actually look at, one thin film with varying nickel thickness and find out, it turns to be, it seems to be a critical thickness below which the transport's relatively straightforward. So it's a little bit of a miracle that this actually works. My sense is that after you go through 1 or 2 cycles, there are enough defects so that things can go through various ways.
Yeah, after the expansion, you can see that.
Yeah. So in the case that we've done this with silicon in CEES 1, and we could create anode structures which would cycle for 1,000 times. But when you look at them, they look like somebody had stepped on them. So there are a lot of cracks and so forth. But nevertheless, they seem to hold together. So.
Yeah.
I guess you can get a sense for how uniform the layers are during this
Mm-hmm.
discharging. So that, I guess that suggests that the lithium is diffusing as a solid state diffusion through all the layers.
Yes, yeah. The lithium is right. So the active, it's going through these active materials, but it's getting through the metal as well as the active materials, and so there is some kinetic limitations, and that's, I mean, the fact that the Bragg peaks are disappearing, here indicates that it's not actually completely uniform, but is that what you were asking? Yeah.
It's solid state bulk diffusion.
Yeah, that's what we think is going on. Yes.
Okay, thank you very much.
Thank you. And